We continue with basic image processing and analysis, moving on to VOIs. And the extraction of information from our images relies on these volumes of interest, which we then typically call VOIs. This definition of VOIs constitutes a segmentation of regions, organs, or particular tissue types within your subject, and that can be driven by tracer uptake or by anatomical information if that's available. VOIs in PMOD are built from contours. These are planar polygons, and contours can be defined in coronal, sagittal, and horizontal planes. All of the contours from a given VOI in a single plane are grouped and considered as a region of interest. This is indicated by the lowest slice in our illustration here. A stack of ROIs then becomes our volume of interest. There are many tools available in PMOD for VOI definition and adjustment. They're summarized on this particular slide, which we'll have time to look at later. Where possible, the semi-automated and automated methods are favored, including methods with careful control of segmentation thresholds. But fully manual methods are always available as a backup, for example, where image contrast is poor and automatic methods fail. To demonstrate a number of the typical VOI tools, we now switch to the View tool. Here I will return to the DB load page, and I'll load the original PET3D for the subject PSEG2 that was used in the previous exercise. So in this case, the organs with the most prominent FDG uptake are the brain, bladder, heart, left ventricle, and a number of tumours. And so we can use some of the tumours as examples for VOI drawing and extraction of statistics. If the MIP isn't already active, we can activate that using the button in the center of the image display. The MIP with this inverse grey color table is particularly useful to identify these tumors and to be used as a navigator when we zoom in for the VOI definition. If necessary, we can adjust the color table thresholds to see the image more clearly. Values between 0 and 30 are good for this data. This highlights the activity in the brain, the tumours and the bladder. Now we can go to the VOIs page using the workflow button in the lower right. Since we're working with 3D data, we can start with simple 3D VOIs. And as I mentioned, we'll use the MIP image as a navigator. So we can click on the MIP image in this large tumour near the heart. This triangulates that tumour in the image display, and then we can zoom in using the controls at the bottom of the image display to see that lesion more clearly. Notice that the MIP does not zoom, so it continues its function as a navigator even once we've zoomed in to the image itself. Now we can create a 3D sphere object that will approximately enclose this tumour with a minimal background. In the center of our VOI controls, in the center of the page, we see the sphere icon. In fact, this gives us access to a number of objects, and sphere is the second in the list. The button opens a sphere definition dialog where we have the exact location based on the cursor, and we can define the radius. For this example, a radius of 15 millimeters works well, and then we can create a new VOI definition. Then close this dialog, and we see our sphere on the image, at the moment not correctly located around the lesion. So the sphere can be interactively expanded or translated and rotated even once it's been made into an ellipsoid, as long as the VOI control illustrated here is active. Then we can select the central cursor in the sphere and move it interactively with left click and drag to position it better around the lesion. This is enough for this first example with the sphere, and then we'll move on to other examples. VOIs can then be renamed, so I'll quickly rename this first VOI lesion 1. A number of keyboard shortcut VOIs are available for human oncology analysis. and these can be found in a list of general shortcuts via a right click in the image display. At the bottom of the menu that appears. Here we see 4 pages of shortcuts that you can use in PMOD, and on the final page we see shortcuts for VOI operations, where we'll now particularly look at Control L to create an ISO contour VOI and Control Q to create a peak VOI in a sphere. These shortcuts and their controls are also in the VOI configuration panel on the right hand side. If we scroll down, we see the section for VOIs defined by hotkeys, where we see the search diameter for the Control Q peak VOI method, and then the starting box size and threshold that will be used for the Control and L method. Using the MIP, we can select the tumour near the liver. Left clicking in the MIP will take us to that location. We can see that it rather has 2 lobes, and now we can focus on the larger of the 2 parts. Use Control L to create an automatic ISO contour VOI around this lesion. We see the starting box defined in checked illustration around the lesion, and then we can see the contour in light blue around the lesion itself. Now we can return to the lesion near the heart and use the peak VOI method to make a comparison VOI. Make sure that the cursor is located within the lesion, and then we can use Control Q to create an automatic SUV peak VOI. Again, we see a dashed outline for the search boundary, and then in solid purple pink we see the 1 milliliter Q. So we see the 1 milliliter sphere outlining the SUV peak volume. This will be used to compare the results to our sphere later on. But note that some of the VOI statistics can be overlaid on the image for convenience and to make quick captures. This is illustrated in the right hand side, also in the VOI configuration tab. Now we can turn on peak, and for the currently selected VOI we see VOI peak and the value overwritten in the image. Then we can use the Control E shortcut to make a quick capture. This brings up the capture display dialog, where for example we can choose to add this display to the console so that we can make multiple captures and save them all later on using the console, which is in the lower left of screen. Now we can select the lesions in the right armpit and use some of the ISO contouring controls. Here we see several lesions close together, and so ISO contouring with a defined starting boundary, similar to what happens with the hotkeys, can give us a certain amount of control. Here we can create a sphere around the lesion as a starting boundary, and then we will open the ISO contouring tool. I need to create a new VOI. Then I have access to the sphere dialog again. I can keep my radius of 15 millimeters and apply that to our new VOI definition, and we see that starting boundary around 1 lobe of this lesion that we triangulated. Next, I open the ISO contouring tool. Here we can start by using the default methods. We can give a shortcut for set defaults in the top right, and the default is a percentage threshold. Alternatively, an exact value can be used, and this could be an SUV based value, which we will see in exercise 9. For now we can use the default settings, which is for 3D hot searching without multiple regions or inner holes, and we can adjust the percentage to 45%. So that it's comparable to what we achieve with the Control L shortcut. We see the contour adapt on the image, and now we can confirm the generation of our ISO contour VOI. Another alternative is one-click 3D isocontouring, where the pixel we click on becomes the threshold. This is less reproducible, but it can be useful for quick exploration of the data. Again, we can create a new empty VOI. Then we can select this 3D hot isocontouring tool, and then we click on the boundary of another lesion, defining that as the threshold and creating our contours. We can now calculate the statistics for these VOIs. Next to the statistics icon in the top right of screen, there is another configuration icon where we can configure the selected statistics. Here we can choose which particular statistics will be calculated for our VOIs, and we can keep that group as short as possible to speed up the calculations. For now, average, standard deviation, volume, and max are interesting for these lesion VOIs, and when we confirm that dialog, the statistics will be calculated. The statistics viewer is opened, and these basic statistics are shown. Averaged corresponds to our SUV mean eventually, and likewise we have max. In the top left of the statistics viewer, we can switch the units directly between kilobecquerels per cc and SUV when that information is available. So here we see the units change to gram per mil for SUV body weight. Now we are directly seeing SUV max values for the VOIs we defined, and by selecting averaged, we'll be getting our SUV mean values. The results can be saved in PMOD's built-in .voistat format, or using the shortcut in the top right, they can be copied to clipboard for easier transfer into programs like Microsoft Excel. In fact, the selected statistics is the default mode for calculation of statistics, and the statistics menu can be expanded to see other options available. The statistics that we get by using this access to selected statistics will match what we have in the configuration that we just saw.